Hi, in this video I'm going to show you why t of 0 is equal to 0, and here the 0, I put the error on top of it, in represent 0 is a vector. Okay, and if t is a linear transformation, so this seems obvious but not quite. So let's start with the linear transformation definition. So this is the definition of linear transformation from V to W. So if VW are vector spaces over the field F, a linear transformation from V into W is a function t from V into W such that t of C alpha plus beta equal to Ct alpha plus T beta for all alpha beta in V and all scalars C in F. So you can think about the vector spaces here, or it's a set of vectors basically, and the scalars C in F in the field F. Scalar C, you can think about F is a real numbers. Okay. This is a definition. For the definition, not much you can do. We define it this way. Okay. So now, how to show that t zero vectors, and we know zero vectors. Zero is in W, and also zero vectors in also in W. Okay. So to begin with, and remember the vector space V and W all contains vectors only, and the field F contains scalar. So zero vector, okay, is a vector that is zero. It's not a scalar zero, so they're different. Okay. Now, how to show t of zero vector is equal to zero vector? Okay. Again, from the definition, we try to find a clue. Okay. So we start out with the transformation t of 0, and eventually we want to show this is equal to 0 vector. Okay, not 0 scalar. Okay, because the scalar 0 is not in the vector space W, because t is a function from V to W. Okay, so t of 0 should be a vector, and that vector is in W, as I mentioned here. Okay, now we start off with t of 0 vector, and 0 vector can be written in this way because we want to use the definition t of C alpha plus beta. So how do you rewrite 0 vectors in terms of C alpha plus beta? So here's the way you want to try. So we know that C is a scalar, and all scalar of C in F will meet this equality. That's the definition of linear transformation, and we know T is a linear transformation. So we choose C equal to 1. We choose C equal to 1, the scale equal to 1. So it's 1 times 0 vector, okay, plus 0 vector is still 1 0 vector plus 0 vector. So 0 vector plus 0 vector is still 0 vector. So this equality remain the same. So we maintain the equality. Now, once we rewrite the form 1 times 0 vector plus 0 vector, and this essentially this is alpha, and this no sorry this vector, this is alpha. We basically choose alpha and beta for all alpha beta in V. They both 0. Okay. Now we can follow the definition. The t1 times 0 vector plus 0 vector is actually 1 times t 0 vector plus t of 0 vector. Okay. So 1 times 0 vector, I don't know what 0 t of 0 vector is, but I know there's a 1 t of 0 vector plus t 0 vector. So this turned out to be 2 of that thing, t of 0 vector. Okay, so from the left hand side we have t of vector, t of 0 vector equal to 2 times t 0 vector. So the only possibility is you can move the t of 0 vector to right hand side to 0 vector. So we go to the next page. So the 2t 0 vector minus t of vector. Okay, so if you move the t of 0 vector from the left hand side to right hand side, we swap again. And the right hand side should not be 0 scalar, it should be 0 vector, because this we're talking about the vector uh, operations or computations. Okay, so if you have 2t of 0 vector minus t of 0 vector, so 2 times 1 is equal 1 left. And I don't know, again, I don't know what it is, but this guy, the left hand side is t of 0 vector and the right hand side is 0 vector. So that get the proof. Okay, gets a proof. So that is why the t 0 vector is 0, but this is based on t is a linear transformation. Okay, if t is not a linear transformation, you cannot get to this result. Okay, so now let's see if t of c1 times alpha 1, whether it is equal to c1 t alpha 1. Okay, again, from the definition, we can choose beta equal to 0. So basically, this is equal to c1 alpha 1 plus 0 vector. We can choose beta equal to 0, and this will remain the equality of t c1 alpha 1. Okay. Now we apply the linear transformation. By definition, this is going to be c1 t alpha 1 plus t 0 vector. Okay, and again, t 0 vector is a 0 vector, which is proved earlier. So this is going to be c1 t alpha 1 plus 0 vector. And 0 vector plus anything is anything. Okay, so it's c1 t alpha 1. So that we get this proved. Okay, now we take a look at, if we add another term, c2 alpha 2, okay, whether it's equal to c1 t alpha 1 plus t c2 times t alpha 2. Okay, the answer is yes based on the definition. So from here, okay, we just let this guy to be beta. Okay, so from definition, this will be equal to t c1 times t alpha 1 plus t beta, and the beta is c2 alpha 2. Okay, and then we now have to decompose this from the previous one. The previous one we say t c1 alpha 1 is c1 t alpha 1. We just use that rule. We just create it again. So it's t alpha 1 plus c2 t alpha 2. So that will be equal to the right hand side. Okay, so that's get proved. Now let's move on to this one. If you have n terms, okay, c1 alpha 1 plus c2 alpha 2 all the way to cn alpha n, will it be equal to c1 t alpha 1, c2 to t alpha 2 all the way to cn t alpha n? The answer obviously is yes. So you can do it yourself, but I give you some hints. So we let this to begin with. This is beta. Okay, so the first thing we try to convert t c1 alpha 1 plus beta, the whole thing, and then you get this one factor out plus the rest. So you can eat one term at a time all the way. Okay, and eventually you get this beautiful term expression. All right, so that's about it. Thank you, and if you like my video, please subscribe or thumb up. Thank you.